All right, are we ready? All right. Hello, everyone, and welcome to my presentation. My name is Jere Sanisalo, and I'm one of the lead programmers at the oldest living game company in Finland called Housemarque. And some of the games that I've been working on are Super Stardust HD for the PS3 and Detonation for the PS3, and I will be talking about those. So first, like a fast primer on. I will give a fast primer on these games as we progress. Here's Super Stardust HD, and here's Detonation. So it's a zombie shooter game, the later one. So what I will be talking about is more like an anecdotal view of how to make gameplay code and good, preferably good gameplay code, and give some definitions on what I consider to be gameplay coding actually. Then a fast overview of the PS3, because Super Stardust HD and Detonation are for the PS3, and the PS3 offers some unique challenges. And at the end, I will like lay out what we're doing in the current project, which is totally different from Super Stardust HD and Detonation. I actually have enough material here to last for 3 days, so let's hope we can get through this in 45 minutes. All right, so gameplay coding. So the definition that I'm going by here is that it's code that implements the actual game mechanics. This means that what the game engine here is, it's basically a supporting structure that gives the pieces that you use to make the actual game. So game engine contains stuff like rendering, 3D stuff, streaming, all sorts of math libraries, physics even, and all sorts of components that you then use to make the actual game. There are really many ways to go about making like the actual gameplay, and it's quite often a mix of different approaches. So, for example, some are like straight coding, that you type all of your logic in C++ or C# or whatever. Scripting like Lua or custom scripting languages. Then there are many ways of doing like game-specific tools, like state machine editors and all sorts of game-specific things that help define the specific functionality for the gameplay in a specific game. And I've also listed data-driven, because you can actually define quite a lot of gameplay just by adjusting numbers. So actually, for example, in Super Stardust HD, I will get to that soon, but in Super Stardust HD, for example, the gameplay itself is straight coded in C++, but it's data-driven in a way that every specific thing is controlled by variables that the designers can then tweak. So it's always best to choose based on your platform and on the game you're making, and also taking into account on how big of a team you have and how much content there's going to be. If you have a really huge team, then scriptings and game-specific tools become a lot more important than with a really tight, defined small game and small team. So to get to the meat of the issue, I'm more specifically now thinking of multithreading the gameplay code. And multithreading is already quite difficult. There are also all sorts of mutexes, semaphores, there can be deadlocks, all sorts of problems with syncing everything. And the problem here, what gameplay actually brings to the table, is that gameplay is really hard to do in single-threaded fashion already. And the reason is that it's hard to define. And it's really hard to say that move the specific amount and write all of those things into a design document and then have an engineer go and like, yes, I will do this. Fine, and you have a perfect game. So in reality, it means that there's lots of iteration. You need to try, and often when you're iterating, you start to see like totally different things come up. Like, okay, now, what if these enemies aren't enemies? What if they are friendlies? And all sorts of things that actually make it really hard to have a stable code base to build upon, because the code has to live with the requirements, and well, once you iterate, you need to test the things, and designers can be quite harsh in their requirements. They promise at the beginning, no, we won't need the characters to actually have close combat. But then the tone changes in 6 months, and then it's really fun for the programmer. It can be helped a bit by prototyping, making separate prototypes. It can be actually even in a different engine, but still, in the end, you need to have all of the pieces working together. And an important question is why go multi-threaded in the first place for gameplay code, and there are actually some really good big reasons not to do it, and it's quite easy to pick some subtasks like rendering, physics, collision detection for multi-threading, and those are usually quite easy to separate, but what multithreading can put to the table, that you can actually use the power you have on the modern CPUs and even GPUs to make more complex worlds, or even just like more entities, bigger things, more explosions, dynamics, or even better frame rate, because quite a lot of games actually run, at least the consoles, on 30 frames per second. And personally, I believe that the jump to 16 frames per second would make many games better. And ironically, Detonation is 30 frames per second. And multi-threading doesn't necessarily make for a better game. It's just a tool, like everything else, like scripting or well, anything. So you need to consider if you're thinking that is it worth the effort and worth the hassle. But for example, in some new coming mobile devices, there already are multi-core ARM chips. So the single core isn't that high. It doesn't run in that high of a clock rate, but you have many cores, so you can use that as a leverage. And if you have good multi-threaded gameplay code, then you can more easily hit that 60 frames per second mark and make for a better game. So first, before I get to the games themselves, a quick overview, like really quick overview of the PS3. So the important thing to understand about the CPU of the PS3 is, which is the cell chip actually, is that it contains a single PowerPC core, which is hyper-threading, so there are 2 hardware threads, and there are 7 of these SPUs. And SPUs are these separate processors inside the cell chip, and they're actually totally separate from the PowerPC core. It has the SPUs have their own assembly language. They run their own programs. They have their own memory, which is 256 kilobytes. And the only thing combining these two is actually memory access, which with the SPUs you need to make specifically by hand using DMA. That if you want some specific piece of memory from the main memory, then you have to like say, now please DMA start transferring memory from that main memory location to my local memory, and you can actually keep on running the SPU program while the data transfers. But this basically means that there's no L1 cache, for example, on the SPUs, and you have to do that by hand. But they're really good at stream processing, and the instruction set is actually a vector instruction set, meaning that all reads and writes from the local memory happen 16 bytes at a time and on 16 aligned boundaries. And that makes for some interesting code, actually. There is a GCC for this, and if you run normal C++ code through it, it will wreak havoc on your code, but it's actually been good enough for our users. And SPUs complicate multi-threaded gameplay coding a lot, so that's why it's quite important to understand that if on Detonation and Super Stardust HD, where we do use the SPUs for multi-threading some of the gameplay aspects, that you have to take it into consideration from the beginning. So a quick look on Super Stardust HD. It's quite old. I think 2007 was the year when it came out for the PS3. It's this asteroid shooting game where you go on the globe. There's a ship in the middle there, and you shoot these rocks. The big rock chunks are actually consists of something like, if I don't remember wrong, something like 300 to 400 small rock pieces that you can, each of them individually, either shatter all around the sphere or destroy. So in the end, I think the game can simulate something like 10,000 of these rock pieces at 60 frames per second. So the task division on Super Stardust HD, how it went, was that when we were starting, we estimated that the asteroids and their destruction, that you can accurately break them into pieces and do all of that, that would be the most demanding task of the whole game. So we focused from the beginning into getting that split into separate threads. And so the asteroids were, these numbers may actually be a bit wrong, because I can't remember all of them by heart. I think that the 256 pieces may actually be 512, but the point is that all of the asteroids were split into these batches, and each batch contained, like if you spawn like a big rock which has many pieces, rock pieces, that has to be in its entirety in a batch, and we had about 16 of these batches or something like that, and all of these are separate SPU tasks which are run, and the way it's actually done is that at the beginning of the frame it's synced from the last frame, and then that data is read and used by the game, and when the gameplay has finished its slot, so when the rendering side starts, that's when we kick the new SPU tasks live, and all player, enemy, and level logic was actually done single-threadedly, and the reason was that at the beginning the designers thought that no, there won't be that many enemies, but well, in the end there were tons of enemies, and some of them were quite complex. For example, there are these swarmer enemies which use a flocking algorithm, so they avoid each other and they avoid the bullets. And those actually ended up taking most of the CPU time from the CPU update. But it actually worked beautifully that we hit the 16 frames per second, and about half of that, I think, goes to gameplay, rest goes into the CPU side of the rendering. And we actually had to make, and this is actually quite important point if you're making like gameplay heavy games, that we had to make and maintain a smooth frame rate, because we cannot use frame skipping because the update is so heavy that if you run it twice then your game will stutter, you just cannot catch up. So we kind of had to make it run like as smoothly as possible, and also using variable time step wasn't possible. I'm not actually a big advocate of variable time steps because it kind of makes all sorts of things more difficult. For example, I use quite a lot of linear interpolation, like when the rocks come down, they slow down while they get close to that grid where you play, and all of that is done by linear interpolation, and all of that gets a bit more complex if there's a variable time step. So actually, all of the games that I work on actually contain a fixed time step. Then next game, Detonation. Detonation came out actually last December, and it was actually a free for part of this free game offering when Sony failed again with the random number generators and got hacked. So actually there are now, I believe, more than 1 million people who own Detonation. So it's a zombie shooter game where you're the guy there and you shoot zombies with all sorts of different weapons and generally kick ass a lot. So the requirements from what we started from was that we had to have hundreds of zombies, and this is something that never changed. We first had a goal that yes, 1,000 live zombies, all animated, all skinned, and so on, and physics for everything. And well, that was a bit optimistic. That we spent like 2 months creating our own physics engine because we thought that we could beat Havoc. In the end, we couldn't, so we bought Havoc. And at the end, we ended up with 144 live zombies that can be visible and animating and running at the same time. That weird number actually comes from well, it should be dividable by 16, which means that it's easier to slot into the SPUs. And we first had like something like 256, but then we started to optimize like how many skinned characters can we push through the GPU. And went down to 144. And the game actually has lots of complicated behavior. Like characters may make game really complicated. For example, here all of the characters have reaction animations and all sorts of like getting up animations, all hitting animations. When they walk, their feet have to be synced with the movement. What the physics engine gives us, and there are like tons of different details which come to play after you decide that yes, we will have characters in a game, and also the logic for the characters suddenly comes a lot more complex because you have to time it with the animations, you have to time it with the physics, and have all of that somehow functioning. So yeah, and it was actually a surprise to us that how complex games can get when you have tons of characters, and also well, this came a bit like as a feature creep that the environments had to have lots of dynamics like opening gates and moving lights and all of that. That it kind of came that I made a simple way of animating a light, and then someone said, could we have that helicopter there so that its propellers would rotate, and after that it came that, hey, could we have those gates open when there are no zombies near, and suddenly we had like all of the big things what you have in a game, and this wasn't actually super planned, but we made okay in the end, I think. And also one big and important thing here is that we had to have deterministic gameplay. What that means here is that if you consider that a frame in a game is only a piece of data, and the game update itself is only a complex function that takes that data and returns a new data for the next frame. That if it's deterministic, that means that given the previous frame, running the update always gives the same results. And quite often people say to me that, well, doesn't that happen automatically? But it's actually surprising how easy it's to break that in a way that the game still works really perfectly, but it's not deterministic. For example, well, when multithreading, for example, two threads may send messages at a different order, and sometimes when receiving messages, you do things immediately when you read the message. So if those come in a different order, the result may be different, but it's still correct. But it's not deterministic then. And the only changing thing here actually is the user input, meaning that what you have on your controller, that's the only changing thing. And you can still have actually randomness in deterministic gameplay. That just means that you have a fixed seed which at the beginning, which you use in the same fashion at the same places. And if you have multi-threaded gameplay, actually, you want to then split that seed into many different generators, so that all of the threads and running pieces will run no matter at what order they run, they will always use the same randomness. And the reason why we needed this was for online co-op. That when we started to think that, okay, we have 144 zombies, all are close to the player, there's no way to use priority tracking or anything like that to sync those, and there would be all sorts of other problems like syncing with checkpoints and all of those, which would need to be special cased. Then we figured that going deterministic is the only way, so we only send the player controls to each other. There will be a minimum of 1 frame lag because of that, and in reality, I think something like 3 to 4 frames. And remember, this is 30 frames per second game. 3 to 4 frames was still really playable, actually. So that makes for something like 200 millisecond lag or something like that for network. And for Detonation, once this whole system was set up, everything actually worked really beautifully. It took something like 2 weeks to set up, and the good thing is that we can now have as many zombies and as many debris and stuff like that in the game, and it just runs with the same bandwidth. And the online code is really simple. It's just a single C++ file. So as I said, it took 2 weeks to set up, and there were some gotchas. I say DirectX here because we run our internal builds on the PC when creating the levels and so on. But for example, for one gotcha was that DirectX by default changes the FPU precision flags for one of the cores, but not for all. You can set it with FPU preserve flag when creating DirectX, but this actually took like a week to track down, while sometimes the floating point calculations went differently. And luckily, we did go with Havoc because Havoc supports determinism out of the box. So our most complex element, in a sense, already had deterministic gameplay. We actually found a couple of really hard to track bugs which took something like 8 weeks to track in Havoc for determinism reasons. So it's not easy to do that. And we had a simple AI that ran these regression tests every night and all weekends. So that it basically played the level, recorded its controller movements, then replayed those movements 4 times just to make sure that it works, and it calculated CRCs for every frame. And multithreading makes the determinism a lot more complicated. The way to tackle was that everything we actually run most of the gameplay in Detonation in the SPUs. So all communication between them goes through message passing, and when a message is sent, the sender ID is attached with that, and when the messages are received, they are sorted based on that sender ID, and there cannot be like simultaneous action with sender and a receiver, so those have to be separated. So it's quite often actually with multi-threaded gameplay, introducing a frame lag is your friend. So you can do stuff now and have the result at the start of next frame. So that's how the message passing worked, that it sent messages now and they were processed the next frame. So the division of gameplay task in Detonation was that 90% or more of the gameplay code runs multi-threaded and on the SPUs, meaning that we have tons of different SPU executables. And the most complex parts, I think, are character updates and item updates. So character updates actually runs three things simultaneously. So there's logic update for the characters, which is run on the SPU. After that is done, there's a world movement update, which moves the Havoc model in the world. And that's run on the main PowerPC core. And after that's done, the SPU picks up back again, and there's animation update because and it has to be in this order because you need to know where you moved and how much, so you can update the animation to match that movement. Then items are done next. There's actually a slight error here. They run simultaneously on PPU and SPU, meaning an item in Detonation in terminology is basically an entity. So anything that is not a character, anything that's dynamic, and it can have any combination of attached sound, events, particles, meshes, collision meshes. It can be dynamic in the world, and it can have like shadow lights and all of those. So the item updates are mainly run on the SPU, but then the CPU at the same time does things with the spawns meshes for our engine and so on at the same pace as the SPU is updating. And then physics, well, that's Havoc. And then there are smaller tasks like level logics and proximity detection and so on. So everything actually, the way Detonation was done, that everything is done using a custom state machine editor, and all logic is done there. So what the programmers need to do is only define the specific things like test if something is near, move somewhere, or spawn a new item, kill a character. These blocks that then the designers could use freely to create the gameplay. And the good thing is that once that was done, it was made deterministic, so out of the box. So there was no way that designers could actually break determinism using that editor. And that also allowed for a really fast iteration, because we had this system where you could update the scripts on the fly. So you could just like make a change, hit the button, make a change, hit the button, and you would see it continuously on the running game what happens there. So here's a screenshot for our from our state machine editor, just to give a taste. So those balls are states, and all of those lines are transitions to different states, and the lines that go nowhere are quite often transitions which have logic in them, like they have tests and things that actually do something. I believe this script is for the player character. And we have similar things for items and animations. And to move on, I hope I have enough time. So the current stuff, so that was Detonation and Stardust. So the current things, what we're working the next game, it won't run on a PS3, but the platform it's running on, it has symmetric cores, like the PC or Xbox 360. So that simplifies things a bit, but our design for the game requires tons and tons of moving entities that need to explode, and we need to hit 60 frames per second for that game. But the amount of different types of gameplay elements is a lot less than in Detonation. In Detonation, I believe that there are something like 16 types of characters and something like a couple of, no, I think 1,000 different types of items which are defined there, and there are a lot less on this gameplay, on this new game. So I decided to go with the Super Stardust HD way of coding the gameplay itself by hand and proposing hundreds of these tweakable numbers to designers that when they start whining that something is not perfect, I just say to tweak the numbers and be happy. And it actually has worked out pretty well. But we still needed to iterate a lot and somehow have the gameplay be multi-threading and keep that in check somehow. So first, when I started to think about this, I considered a traditional job system where you have tasks, you define tasks, you have a function that runs the task, you have some resources, and you have dependencies to other tasks. And then you have the task system to run those in a dependency order. But it quite fast became obvious that this would become really cumbersome. Defining the tasks would require a lot of syntactic sugar, and keeping the whole thing in check. It just felt nearly not as agile as I would want gameplay code to be. So I started to look for other programming languages and systems for inspirations. So, for example, in Erlang and Google's Go language, there are these processes or Go routines, which you can have like thousands or millions of. And so I started to think that if I had something like that, how to do it. So for example, if you need something in those languages, you can just block and wait until that specific resource is available. So that appealed a lot to me. So I started to think that could we do this somehow in C++? The problem with operating system threads is that they're too heavy to have in a big number. For example, there are some limits, I believe something like 32 threads max on PS3, and all of those are switched periodically by an interrupt, and we need to hit 16 frames per second, so we have only 16.6 milliseconds to do it in. So operating system threads are not a go, but somehow that still appealed to me. So the solution came in the form of fibers. So if you don't know what fibers are, they're kind of like cooperative user space threads, which the programmer you yourself implement and control on your own. And this is actually supported on all of the platforms we develop for PC, PS3, 360. So what a fiber really has, it's quite simple. It has its own stack. So if you have a fiber, the fiber has its own CPU stack and its own CPU registers. And the registers always contain the running position and the stack pointer, to name a few. So when you do a fiber switch, all you need to do is record the current registers in the fiber and read the new registers from the other fiber, and that's the switch. And it's really lightweight, and you can have tons of these. The downside is that you need to do the handling yourself, but I was actually more than fine with that because it allowed me to customize for this specific behavior really well. So the way I started to combine fibers with this task thing is that each task is made to be a class, and that class is also a fiber. And a task is either dirty or non-dirty. So at the beginning of a frame, all tasks are marked as dirty, and when the update method has finished, then that task is not dirty. And at the end, we want all tasks to be not dirty, meaning that all tasks have finished their update, and then the frame is done. So what a task can do on its own isn't that interesting, but it's more interesting when a task requires something from another task. So if a task requests access to another task, for example, player renderer requires a mesh manager which renders meshes, and both are tasks. When that pointer is requested by the player renderer code, there's a check. is the mesh manager dirty? If it's not dirty, then the pointer is simply returned. If it is dirty, then the current task will be marked as dependent on the other tasks like mesh manager here, and then there's a fiber switch to some other task which we can run now. And all task dependencies, the upshot from this is that all task dependencies come automatically and they're computed on the fly every frame. And cyclic dependencies here will deadlock, but we have on the PC build tons of security checks which look for even possible deadlocks or cyclic dependencies, and that has worked fairly well here. So, so to give a bit of like primer here. Here, for example, there's the task class from which you inherit from, and the way we've done it, that when you create a class, instantiate a class that is derived from the task class, then that is automatically added to the scheduler, so you don't need to do anything else than to create your subtasks, and that's it. And each task has a pointer to a task list. For example, here are some pointers to player input task, player renderer task, mesh manager task. And this helps in a way that every task can see every other task and pick from those what you want. And this helps gameplay programming a lot, actually. So let's hope we have time to finish this. Well, for example, here's a player input task and player task. So the player input is marked to run on main thread because we need to sync that with the rest of the engine, and then there's the update method which reads them, and then there's a get controls function. So the player really wants the player input, so it does a get call there. That automatically does the Boolean check that is the task updated and does a fiber switch or not, depending on what is required. So that all of this comes automatically, and the player then has an accessor function for get matrix, which gives the current matrix. Then we have a mesh manager, which again needs to run on the main thread, and then there's an add mesh function, which is a way to push things into the mesh manager. This actually is one of the points. Reading from task is safe, but writing to it, you need to take care of multithreading. But actually, even having the system automatically take care of your dependencies eases that up a lot. And then we have, for example, a player renderer here, which takes a pointer to the mesh manager, takes a pointer to the player. There are the checks done at each step, and if it's dirty, then it automatically goes into a wait mode, and other tasks are run at the same time, and then the mesh is added to rendering. So the pros actually is that the code becomes suddenly really clean, that you can have these separate things be totally separate from each other, and then on demand, like, okay, I want access to this here and access to that here, and all of the things like with multi-threading or fibers and everything is abstracted away, so that the code is just that you have an update method and you want to run that through, and if you want access to something, you just get it and you automatically get all of the syncing for the threads and fibers. And it's really easy and fast to iterate. That there have been like really complex things here. What designers have wanted, like total U-turns, and all of that has been really easy. And this is actually quite fast. It's ON complexity to go through the whole dependency thing. And you can make these dependencies also conditional, that you can get the pointer inside an if statement, and then for most of the frames, that dependency isn't there, but sometimes it is. So you can do all sorts of funky stuff really easily. Also, many of the multi-threading problems disappear because of this. You have total sync now between tasks. And for reading, this is enough, but for writing, for example, the mesh thing, you need to take care of the multi-thread aspects here. And it's easy to make fast cache coherent code with this. So you can have like, for example, you can have like an enemy manager that runs all enemies for example. And so the update of that single thing runs all enemies. So you can have all of those in an array and run through them one by one. So you can have like really fast cache coherent code with this. And even the access source then will just gain pointer to that array, and you can read all of that so you don't need to make all enemies separate tasks. You can choose your own size or split for the tasks, how it feels best. And it automatically scales according to load, that if there are spikes, then automatically the dependencies on the other cores are run and solved for you. So some of the minus points are that there are still sometimes that we need to handle collection of data, not just reading. For example, the mesh manager case here. So atomic counters and interlocked primitives are actually a really good thing here. So for the meshes, for example, there's a huge array which using atomic counters you can really fast and easily like pick the next slot and write things there. And actually a lot of this is already in our current engine abstracted away using these template methods that we can easily just program it once and use that for every type of message or spawn command or mesh or whatever we want to. And for tracking things like attached sounds or particle effects, we have again a templatized helper function that when you update that, it does the task dependency at that point. The good thing here is that you can at any point do a task dependency and the fiber switch will just work. And the other thing is that some tasks need to run on the main thread. Our engine is actually single-threaded, which means that there's gameplay, there's rendering. So that means that we cannot add new meshes to the rendering while the renderer is actually working. So we have a lot, like you saw here, we have these flags that tell that, okay, this is a main thread tasks, and those are the only tasks which are run on the main thread, while all others are run away from that. And you don't want to make the main thread tasks be dependent on the things that might take a whole frame to run, because that will make for really inconsistent frame times. But we have found that this is not actually a problem, and there are not that many main thread tasks here. So the current feelings for this system is actually that it's working really, really well. The game is actually currently in quite a good state, and this system has worked perfectly. We're constantly hitting only the GPU bottleneck, and the CPU just keeps on working, and I'm actually quite amazed that with the amount of stuff that we're throwing at it, that it just runs happily along and does all sorts of collision things and all of those, and there are not a lot of gaps between. So currently we have something like 160 tasks, and I estimate this will raise about 200 by the time that the game's done, and about 10 of those are running on the main thread. So there are things like mesh rendering, particle effects, audio systems, player input, to name a few. And currently in the game, on our main thread, the gameplay only takes 2 to 3 milliseconds, and the rest is free for the renderer to use. And actually, one future development here could be that the renderer would be combined with the same task system, and then you could have a renderer that also scales perfectly with the gameplay code. But that's quite a bit of refactoring work, so we haven't done that. And 2 to 3 milliseconds for gameplay, I think, is pretty astonishing. And the rest of actually the 16.6 milliseconds for the other cores is completely dedicated then to gameplay code. And we're hitting the 60 frames per second boundary constantly on the CPU. And here is a really blurry and messy image of the dependencies and this was taken 6 months ago, so this is only something like 80 tasks. Each of those is a dependency from the code, so it looks really messy. Here's a close-up from one part. The thing is that when you look at the code, it's really easy to see what's going on and what's dependent on what, and we have the automatic checking to make sure that nothing breaks. But if I was asked to do all of this by hand, there's no way. So this system has so far proven itself above and beyond. And I think we just about made it. Are there any questions or anything you want me to clarify or talk? Right, I see a hand there. Or do I see a hand? No one? All right.
Could you maybe give some examples of what those tasks could be? You gave some examples, but I still don't quite understand what kind of all types of things you can do with those tasks.
Well, everything is tasks. So all gameplay is tasks. I can start listing this. Player is separated into few, so there's player logic update, player world update, then there's player renderer, which is separate from the player logic update, so that once the player renderer only adds the player mesh to the rendering, but by splitting that into a separate task, we can then more easily run other tasks which are only require the logical information from the player, not the fact that it's rendered. Then there are collision collection, collision detection, audio systems, all enemies are grouped into these. Level logic is actually a couple of these tasks, so every single part of the gameplay is done with tasks. There's nothing else except the tasks. So the point is that it's the whole gameplay is split into the logical elements what you feel are big or small enough. And I quite often do the renderings as separate small tasks because the fiber switch is so fast that we can remove the bottlenecks of that pause that we would have like extra dependencies there. Does that answer your question? So, anyone? All right.
This is more of a question about like issues with the tasks which require double buffering. Like for example, if you want to thread the renderer, you'd most likely need to double buffer a lot of the stuff because usually Direct 3D can only be accessed by one hardware thread. So anything you'd want to split into smaller tasks with related rendering, you'd need to double buffer all the data and get a one frame of lag. But do you have any other systems like that right now which require you to double buffer all data?
Well, I think the only point where I have double buffering is actually the rendering. That's the only point, because all others are done so that the messages and all sorts of like spawn enemies, all of those are collected using the atomic counter and then run or flushed by the update. So basically, I have this template that is many can write, but only one can read. And the reading and writing never happens at the same time, so it simplifies that pattern actually quite a lot. But there's not that many places where double buffering is required by this newest system. But for Detonation, everything had to be double buffered. So every item, every character update, all of that was double buffered.
So is this fiber system totally platform independent, or do you need any special hardware? So can you use this for every platform like iPad or PC or consoles?
You can. The theory is platform independent, but you either need to have the fiber library from the operating system or make one yourself. I basically already laid out what happens there. You just allocate your own stack memory for the fiber, and then you have some piece of code that can read or write the stack, the register set, and that's it. But for PC, 360, PS3, or for all of these, the fibers are already implemented, and you can just use them out of the box. The libraries are there. And the concept is fairly simple. All right, so I believe that we're done now. All right, thank you for listening.